at this state space model to transfer function conversion. Okay, so these are the two equations for the state space model. X dot is equal to X plus BU, Y is equal to CX plus DU. And then we derived the relation between the transfer function and the state space model, and it is of this form. Okay, so you have the A matrix, B, C, and the D matrix here. And then we took a numerical where A is given as this, B is this, C is this, D is this. So what is the transfer function? So we found out that the transfer function is nothing but S plus 3 divided by S square plus 3S minus 2. Okay, so this is what we have got. So what are the poles of this equation, transfer function?
-3 and 2.
-3 and 2. Is it so? What is the equation? S square plus 3S minus 2. So this will be 1 S square plus 3S minus 2. What is the root? Minus 3.56 and 0.56. Correct?
Oh, yes, yes.
Okay, so it's not
Got it, sir. Got it.
3 and 2. Okay, so you have to solve this quadratic equation for the roots. Minus 3.56 and 0.56. So,
Yes, yes.
okay. Now, that is the poles of this equation. So, the poles are at, minus 3.56 and then at 0.56. Okay, so these are the two poles of this transfer function. So minus 3.56 and 0.56. So another way of getting this roots is, this is the problem which we have taken, A, B, C, D. So if you find the eigenvalue of this matrix, okay, if you find the eigenvalue of this matrix, let's find out the eigenvalue of that. Okay, so let's define A is equal to 0, 1, 2, minus 3. Okay, so that's the matrix which we have defined. And how do you find eigenvalue in Matlab? It is Eig and then the matrix. So what you get here is the eigenvalues. Okay, so 0.56 and minus 3.56. Isn't this similar to the poles? Isn't it?
Yes, sir. Yes, sir. It is.
Yeah. So what you see here is, what you understand from this is eigenvalues of A matrix represents the poles of the system. Okay, eigenvalues of this A matrix represent the poles. Okay, so if you see this, A is equal to, it was 0, minus 1, 0 plus 1, 2 and minus 3. How do you find the denominator is? Um, you can take it as a square plus, this is minus 3, so it is plus 3s. This is plus 2, so this is minus 2. Okay, s square plus 3s minus 2 you get from this bottom row. If you look at these numbers, so there is a, this is another way of finding out what is the denominator of the transfer function.
What is the coefficient of s square? So then it will be 1. Like
Yeah,
we have to consider that.
coefficient. Yeah, this we have to consider. So always one higher order must be there. Okay, and
No,
then
no. So is it from the matrix there? We have a1 to write as 1.
yeah, what I am saying is this is for s, okay, and this is for the s power 0, but s square you have to consider. Okay,
Okay.
so this is another way of writing this. Okay, so this always the trend will be like this: s square plus 3s minus 2. Okay, so even if you don't understand this one, it's okay. Since you use this formula, you can still get the transfer function. Okay, the shortcut to that would be to use that as s square plus 3s minus 2. Okay, to get the poles of that uh, transfer function. So what we understand is eigenvalues of A matrix represents the poles. So this is the main thing that is required here. Okay, this is important. Eigenvalues of A matrix represents the poles. Now with poles, what we can define? What do we understand with poles? What is the main thing we talk about when we look at the poles? It is, what do we talk about when we talk about poles?
Stability, sir.
Stability. Okay, we talk about stability because poles define the stability. Now, why are we doing all this? Because we want to design a controller. Okay, we want to design a controller. Now that controller is not PID controller. Okay, not PID controller, some other controller we want to design. Okay, so for that we know that A matrix defines the poles. The eigenvalues of the A matrix defines the poles. Now, if we can modify this A matrix, then we can change the poles. Okay, what you are doing in the um, root locus editor, actually when you find the PID values, that is KP, KI and KD values, what are you actually doing there? Suppose if it's only a P controller, say, okay, suppose only a P controller, forget about I and D. What are you doing in that actually? Any idea? In the root locus editor, in root locus editor, in the root locus editor, what is it you're doing? Any idea? Yes. You've forgotten? Say this is a transfer function s plus 1 into s plus 2 into s plus 3, say. Okay. Now, if you want to control this, okay, so what are you doing with this when you change the value of kp? What is that? What is changing? What are the poles of this transfer function? Open loop poles.
-1, -2, and
-1, -2.
-1, -2, -3. These are open loop poles. These are open loop poles. What about closed loop poles? How do you get closed loop poles? How do you find closed loop poles?
So there's an unity feedback. So it still remains the same.
Closed loop poles. See, what is a closed loop transfer function equation? It will be kp divided by s plus 1 into
S plus
2
2, S
into
plus
s plus 3.
3.
Okay.
Yes, sir.
Is this all? Is this the closed loop transfer function? Look at this and tell me what is a closed loop transfer function. What is a closed loop transfer function of this? How do you find out the closed loop transfer function of this? No answer. Hello.
it will be gain into, will be GS into GC, 1 divided by GS into GC into GS divided by 1 plus GC into GS. Sir.
That you have to tell. Okay, fine. So this is 1 plus kp divided by s plus 1 into s plus 2 into s plus 3. Okay. So what is the transfer function of this? What do you get? So if you take 1 here, it will be s plus 1 into s plus 2
Will
into
be KP divided by S
s plus.
plus 2 into S plus 3 plus KP.
What is that? Kp divided by
S plus 1 into S plus 2 into S plus 3 plus KP.
plus kp. Now, if I change the value of kp, will the closed loop poles change? What happens to the closed loop poles? Will it change or not with kp?
No, sir.
No. Suppose kp is 1. Okay. You get some equation. Suppose if kp is 2, you get some other equation, no? Will the closed loop poles be the same?
Oh, no, sir. No,
See,
sir. No,
it will
sir.
be
Correct.
s plus 1 into
Thought that has only the numerator. No? S plus 1 into S plus
s plus 2 into s plus 3 plus 2 equal to 0. Okay, so the roots of this equation will give what? The closed loop poles for kp,
poles.
for kp equal to 2. Okay, do you understand this? Okay, so if you change this kp, the closed loop poles are going to vary. Okay, so is that not what you do in root locus? If you look at this root locus, see you have two poles here, one at -2 and one pole at 1. Okay, so these are what? Open loop poles or closed loop poles? 1 and -2.
Open loop, sir.
Open loop poles. What is this magenta color one? What am I moving? What are those called? What are those called?
Those are the
Closed
closed
loop.
loop
No,
pole.
no.
Those are the closed loop poles. For what value of k that I can get from
Root loc design.
edit compensator? If I go, I can get the k value here. Okay, if I keep changing this, if I keep changing, then the k will change. Okay, so the closed loop poles I am changing. Okay, with k, because k is changing, the closed loop poles are changing. Do you understand this?
Yes, sir.
Yes, sir. Sir.
Okay, so that is what is this here. When kp is changing, this thing will change. It won't be 2. If you increase it, this will increase. Okay, so when this whole equation equal to 0, you find the roots. The roots will be different for different values of kp. Okay, fine.
Yes, sir. Sir.
Now the disadvantage with this root locus is you can move only in this direction. Okay, in along the loci. Okay, along the points only you can move. Can you move it upwards? Can you move it in the y direction?
No, sir.
You cannot move. Okay, it will not move. So it will move only in this direction. Okay, so what the state space model gives you is, it gives you an option to place the poles anywhere you want. Okay, root locus, what it does, it limits the desired pole positions. Okay, so if I want to place this pole on this uh, real axis, it is possible for me with root locus. Okay, if I want to place it on the imaginary axis, is it possible? It's not possible. Okay, in this case it is not possible because I can only move along this line. Okay, so state space model gives us the option of placing the poles wherever we want. Okay, so when you're able to place the poles wherever you want, what is the advantage that you get? what is the advantage that you get? These poles define stability, right? Poles define
Yes,
stability.
sir.
So they also define how the response is. Okay, whether this is, response is faster, slower, okay, whether there is overshoot and all those. There are many things that these pole positions will define. Now, if I'm able to place the poles wherever I want, then what am I doing? I'm able to control the response. Correct?
Response as well as stability of the.
Yeah, response as well as stability of the system. First comes stability, second is the response. Okay, so if I am able to place the pole positions wherever I want, then I am controlling the system. Okay, so that is the meaning. Okay, that is what we have done in the root locus as well. But in root locus, the thing is, we can only move the closed loop poles only along the root loci. Okay, so along those lines only you can move, or along the curves you can move, but you cannot move wherever you want. Okay, but in state space model, you have that freedom of placing the poles wherever you want to get the required stability and the response. But where you need to place the poles, that is not defined. Okay, that you should decide where you want the poles to be. Okay, based on the kind of response you want, based on the kind of stability you want for the system, you define where the closed loop poles must be. Okay, but uh, the state space model will not tell you where exactly to place the poles. You need to tell where should we place the poles, and it will place the poles there. Okay, so that's the idea of this state space model. So basically what you're trying to do is you're moving the closed loop poles. Okay, you're moving the closed loop poles. Now, in this transfer function, s plus 3 divided by s square plus 3s minus 2, is it stable? Is the system stable? S plus 3 divided by s square plus 3s minus 2, is the system stable?
No, sir.
Why no?
Because 0.56 it is.
Yeah,
Uh,
0.56 is on the right side of the S plane. Okay, so that is why it's not stable. Now, where if I place the poles, will I make the system stable? Okay, instead of -2, probably +2 would be a better choice. Okay, so that's how you identify which pole to move and where to move. Okay, you need to move this pole 0.56. Okay, you need to move this pole towards the left side to make the system stable, and that is the action you need to take in order, if at all you want to control this system. Okay, so that's what we will be doing now. Okay, so quickly we'll see this. If a is equal to 0, 1, 2, minus 1, okay, b is 1, 0, c is 1, 0, d is 0. What are the poles of this um, transfer function? What are the poles? This will be s square. What is the denominator? Denominator equation, s square
S square plus s minus 2.
minus 2. Okay, equal to 0. If you do, you get s is equal to minus 2 comma 1. Okay, s square plus s minus 2, if you do, you will get s is equal to minus 2 comma 1, where this is the problem. Okay, so since this is positive, the system will be unstable. Now what you need to do is you need to change this A matrix in such a way that you get the desired poles. Okay, what is the desired pole? Desired
The
pole.
negative.
Okay, suppose I want it as -2 and -1. Okay, I want it as -2 and -1. So what changes do I do to this matrix to get this one? Okay, that is what we'll be looking at. And why we are focusing only on the A matrix and not B, C, D? Because A matrix, the eigenvalue of the A matrix gives the poles.
Poles of the.
Okay, eigenvalues of the A matrix gives the poles of the transfer function. Okay, so that's why we want to modify this A matrix in such a way that instead of -2 and 1 being the pole, I want the -2 and -1 as the poles. Okay, if I do that, then I can make the system stable. Okay, so what is this concept called? This concept is called as pole placement. This I have not taught you exactly how to get this yet. Okay, I have not taught you the method, but the method name is called as pole placement. Okay, so what is the meaning of this pole placement? You are placing the desired poles in the required places. Okay, so you don't want -2 comma 1, but you want -2 comma -1. Okay, so instead of this 1 you put -1, and this is called as pole placement method. How we are going to do? You are going to modify this A matrix in such a way that the eigenvalues of A will change. Okay, eigenvalues of this matrix will change, because eigenvalues will change means the poles will change. Okay, and that should change to -2 comma -1. So this is the desired pole. Okay, so you define it. Okay, you define the desired poles. Okay, you should define this. What is the desired pole you want? You want -3 comma -1 or -4 comma -2, whatever position you want, you define it, and then you modify this A matrix in such a way that you get the desired poles as this. Okay, and that method of controlling the system is called as pole placement, and we will discuss the method in the next class. Any doubts? Are you finding it difficult? Are you finding it difficult?
So can you just repeat what you said? I just got a call, so.
So here what you do is, in this the poles are -2 comma 1. Okay, so 1 is a problem. So instead of 1 you want the desired poles to be -2 and -1. Okay, you define these desired poles, and to get this desired pole you modify this A matrix. Okay, you modify this A matrix in such a way that you get the desired poles as -2 comma -1, and this method is called as pole placement. Pole placement means you are able to place the poles in the required place, in the required position. Okay, your desired position. So -2 comma -1. Okay, this is my desired position. So you are able to place the poles in the desired position by modifying the A matrix.
A matrix. Yes, sir.
Okay, so this is the concept of pole placement. The advantage compared to root locus method is, in root locus method, you can move the poles only along the root locus.
X-axis.
Okay. Okay. Only along the root loci. Okay. So what is root loci? You would have seen it, right? Like this lines will be there.
Locus. Yes, yes.
And then like this it will be there. Okay, it can move only along these. Okay, suppose if I want the pole to be over here, I can't get that with the root locus by changing the gain. Okay, you can add a pole. Adding a pole is different. Okay, but only with the kp value I cannot place the poles here in root locus. Okay, poles will always move along the root loci only. Okay, so it will not, I'll not be able to place the pole over here unless I add a pole there. Okay, so I'm not talking about adding poles, I'm talking about changing the pole positions. Okay, so I cannot do this with the root locus concept, but if I go with the pole placement method, I can place the desired poles anywhere I want. Okay, I can place the poles anywhere I want such that I get the required stability, I get the required response to the system. Okay, and why we are focusing on A is the eigen values of A will give the poles of the system, and that is why we are focusing on A. What is A? A describes the dynamics of the system. Okay, A describes the dynamics of the system. So that is what is A matrix. Okay, so if you see here in that spring mass damper system, this is A matrix: 0, minus K by M, 1 and minus B by M. So this represents the dynamics of that system. Okay, and that is what is A matrix. If you're able to modify this and get the desired poles, that means you are able to control the system. Okay, changing the pole positions to the required place is nothing but controlling the system. Okay, so any questions? Because that method will take some time. The time left is not enough to discuss how to modify this thing. So any questions till that? I'll discuss this method in the next class. So far, whatever we have discussed, any doubts?
Sir, the coefficient of S square. So on what basis we are considering it as 1? Why not 2 or something?
Okay. See, that was a shortcut method what I told you. Okay.
Okay.
Okay. So that doesn't have any basis, but the basis here is
the transfer function relationship.
This one.
Okay.
C into Si minus A inverse B plus D. Okay.
Okay, sir.
This we have derived also.
Yes, yes.
Derived it yesterday. Okay.
Yes, sir.
From that only we have got this relation
between us
model and the transfer function. Okay, and from that only we got this transfer function S plus 3 divided by S square plus 3.
S square plus 3. Yes,
okay, so why we have to write S square is because of this one. Okay, what I told you here was
to find the coefficient of S and S.
Yeah. Suppose you don't have time for calculating the transfer function from the state space model. For example, you don't have time to calculate the transfer function from the state space model. You can directly look at the
A matrix and
you can look at the second row values and write the denominator of
the transfer.
Okay, zeros we don't know. Okay, zeros we don't know, but the poles you will be able to write.
Okay.
Okay, so that's how it is. So I don't have an explanation of why this is 1s square, but this is the shortcut method, so it doesn't have a basis. But if you look at the formulas and derive the transfer function, you get this.
Okay, sir. Okay.
Any other questions? You get a lot of freedom with the state space model, and many advantages, like you can handle multiple input multiple output systems. Okay, so there are many advantages with the state space model compared to the transfer function. So you should be able to write ABCD matrix for different systems. Suppose DC motor, we wrote a mathematical model transfer function for DC motor. Remember? So similarly, we should be able to write the state space model for DC motor. That means we should be able to define what is A matrix, B matrix, C matrix, and D matrix for the DC motor. Okay, so if we go to that level, then you'll be able to appreciate the state space model in a better way than taking some values of ABCD and doing this. This is to learn further how to use this controller. But if you have to learn state space modeling, then you have to take an application and derive the state space model for that. Then you learn how to get this ABCD. Any questions?
No, sir. No questions.
Okay. Anybody else? Is anyone finding the course difficult? So these are in the 5th module, okay, and I have updated all the uh, videos in the Google Classroom. Today morning I did that. The previous pending classes, whatever videos were there, I have uploaded in the Google Classroom. Please refer to that. Okay.
Okay, sir.
Yeah. Okay then. If there are no other questions, we'll continue in the next slide. Thank you.
Thank you, sir.